first. All right, you guys, so in your notes, you guys have some form of, on page 8, here is an image of an upside down parabola, maybe just the right side of it. You know what, this was before this one. Let me do this one first. Okay, a common shape that we use, and you'll see on your homework assignment, is the parabola, y equals x squared. You see that this is just in the first quadrant that we're focused on here. And so what you're going to be given is you're not going to be expected to recreate or draw any of these figures like you see on the right-hand side. Okay, so what you're expected to be able to do on your homework assignment is draw the parabola. So if they give you guys, so very similar to the area problems, I would expect you guys to draw just the two-dimensional image, which is y equals x squared. They'll tell you guys what region bounds the shape that will eventually become your volume, the shape that you find the volume for. So in this case, they'll say, you know, the region is bounded by y equals x squared, the x-axis, and x equals 1, it looks like here. And so what you want to envision is, I still will have you guys shade the region just so you guys know what it is. But what we're going to do is picture, this one is before the above image, but picture that you guys have basically circular discs of radius that are equal. The radius would come from the x-axis and extend above to the y equals x squared curve. Okay, so this that you guys see, that representative rectangle, what happens is if you guys have a pencil, I don't know if you guys can still see me, I can't see you guys, but if you guys have a pencil and you were to tape a piece of paper, like let's say you guys cut off a rectangle and you tape that piece of paper onto your pencil, and you were to spin that, and you had the ability of spinning that paper around, what you create is a circular disc. Okay, so each one of these rectangles, representative rectangles, are being spun about an axis, and they'll tell you spin it around the x-axis or spin it about the y-axis, but we're going to spin these around the x-axis. And what happens as you spin it around the x-axis, if you guys can imagine your rectangle being spun around, you create a really flat cylinder that we call a disc. So over on the right-hand side, you guys see that the discs are formed. And the idea is that we can find the actual volume so long as we make these discs really short, or in other words, really, really thin. So if we go back to the two-dimensional image, you guys will see that these rectangles are not necessarily really small, but we could reduce the width of this so that we have an infinite number of discs. And when we do, the image that emerges for the volume that we initially saw is going to become the actual volume. And we do that through integration, where now these representative rectangles, the dx represents the height of it. You guys, what two-dimensional figure does the disc have as its base? What two-dimensional figure does the disc have as its base? So if you guys took out a disc, you looked at it in terms of a two-dimensional shape, what shape is that? I'm trying to get the, yes, okay. So you are all typing in circle, which is true. Okay, so that's going to become part of our formula. Okay, we're going to envision a circle, and sometimes people like to think of it as cylinders when we're thinking of it three-dimensionally, summing up a bunch of cylinders. I'm sorry, I'm off on another page, I know. So let me go back, and I was wondering if I had, we'll do that one with the washer. So the idea is that we can spin this about different axes. Today we'll spin around the x-axis first, and then we'll talk about what happens when we spin about the y-axis. But a similar concept emerges. This time your discs are stacked vertically, and each one of the heights of the discs, again, if you look at it this way, so before I had my pencil being the x-axis, so if I spun it around, my circular discs were going in this direction, now they're going in this direction. So we can see that each one of the heights of the discs is going to be determined by a really small change in y, or in other words, dy. So similar to area, we're also going to explore how do we do this if we have to switch everything in terms of y. And it's a very similar process to what we did with area. And so down below here, you guys see what it looks like if you were to, oh, that's not it. If you were to envision it with an infinite number of disks going up. Okay, so the other concepts that we'll cover today is what happens if the region that's bounded has a space between the axis of revolution and the region itself. So this was the best one that I could find. And let's see, it all of a sudden stopped moving, but it was moving it before. So let me try to refresh the page. Okay, so the region that's bounded this time is your top function is y equals f of x. Your bottom function is y equals g of x. And so the idea is now instead of spinning just one rectangle, we're spinning two rectangles about an axis of revolution. And what happens when we do that, if there's any sort of space between the region, like there is here between g of x and the axis of revolution, you get an empty space in the middle. And so if we look at each one of the, if we look at the two-dimensional shape that we get from it, we get basically what we call a washer. And so it's the same idea, except you'll hear me saying, what's the big R, what's the little r? The big R happens to be defined by the radius of the outer region, which in this case is f of x. And then the interior radius would be the g of x. Okay, so let's see how we would do this. Again, you're not expected to sketch these figures. I know they're not easy to do and visualize. So let me reshare my screen. You guys, is there a lag in the what you guys are seeing at all? Let me just make sure that's. Can you guys see my notes? Okay, yeah, actually. Let's see that you can. All right. Okay, so at the very top, the disk method part, I'll just have you guys write a quick summary of it. And I have you guys draw these rectangles, but let me change the color here. So if you were to rotate, if you rotate a representative rectangle, so that rectangle that I had you guys draw yesterday, we're going to draw something similar just so we have, we figure out what our orientation is, whether it's going to be about something that's horizontal or about an axis that's vertical. So down below here, as I'm writing that out, you guys can see the rectangle drawn in the regions of the two curves that you have there, which we saw on the applet. So you're going to draw a representative rectangle about a line, and they always have to tell you guys what they want you to spin it about. Today, we're just looking at the x-axis and y-axis, but they could change that. They could say, can you rotate it about x equals 2 or x equals 1 or y equals 2? And those are always horizontal lines. We don't explore any line of revolutions that are not horizontal or vertical in this class. So about a line, often, but not always, the x or y axis. And then I'll have you guys write one more sentence. We form a disk where a disk, and in parentheses, you guys can write, it's a circle basically with a small thickness, which you're going to be represented by, which is, or small thickness represented by change in x or change in y. Okay, so let's go ahead and take a look at this representative area and rectangle on the horizontal axis of revolution. So in this case, they give you guys, they'll give you the area of that they want you guys to use to visualize the region that you're going to spin about the x-axis. What you're going to do is pick anywhere within that region If they want you to spin it about the x-axis, sometimes they'll just draw this little arrow here that's supposed to look like this. Sometimes that's what I draw, right beside the axis that I want to revolve about. And so again, what you're picturing is that this is your pencil, and you've taped a piece of paper to the pencil, and you're spinning that piece of paper about that pencil. Okay, so in this case, I draw this to denote that this is going to be the height of the cylinder or the disc that I'm envisioning, and this is a change in x or dx. And what that allows us to do is then now, if I were to sketch this, and you guys don't have to do this on your own notes, but what you guys are going to visualize is that you're going to have a disk, if you want to think about this three-dimensionally, to which at the top of that function, that y value, to the axis of revolution, that's going to be your radius. Okay, and so if we just visualize that every time we're doing these problems, that when we're spinning it about, we're going to get a disk from it, the formula makes sense. Okay, and so the formula itself is volume is equal to, we're summing up a bunch of circles or cylinders, in which case pi is a constant. So I usually write the pi on the outside. And since this is with respect to x, dx is the thickness of each one of those disks, my limits of integration are going to be in terms of x, where x is equal to a is going to be my leftmost value. So in this particular image, it would be 0. And then x equals b would be my rightmost x value, in which case this would be 2. So similar to area, you're defining that region based off of the x values that you have there. And then what is the area of a circle? The area of a circle is pi r squared. So the formula itself will be r squared, or I'll just write r squared for now, a little r squared. And in a different color, maybe I'll point to the fact that what defines the r is the y value in this case. So if the y value happens to be f of x, sometimes you guys will open up a textbook and you'll see for the disk that the formula is pi f of x squared. So sometimes that's also written like that. I like to keep it simple and just think of it as r, and then visualize the radius is the top of the function minus the axis of revolution. So in this case, the axis of revolution is just the x-axis, which is 0. And at the very end of that, you guys are just going to write dx. Now, if we think of this as the integral as the sum, what you guys are essentially summing up is a bunch of cylinders, right? Pi r squared gives you guys the base of that cylinder. D of x gives you guys a really small change in x, or the thickness or the height of that cylinder. Okay, so then that's your formula for if it's a horizontal axis of revolution. Now on the right-hand side, you guys have what happens if it's a vertical revolution, in which case you guys are going to picture this is your pencil. You've taped a piece of paper to that pencil, and now you're spinning it about a pencil that is held vertically. So your axis of revolution is vertical. And so what emerges is you get a cylinder, not drawn to scale here, where this is your radius. Sorry, that is really awful. So let me erase that. Sometimes it helps to draw the other side of it as well. But so basically each one of your discs is going to look like that, where the radius of that disc is determined by the x value of your function. And so I'll talk about, like, now what we're going to do is switch everything that was in terms of x. So your equation you guys had in terms of x, now we're going to rewrite in terms of y, just like we would with area. Okay, so this is a vertical axis of revolution. So the formula itself, if we don't think of it any differently, then I just think of all my disks as pi r squared. And so it doesn't make it so that it's another formula to memorize. You just have to keep in mind that your limits of integration now are y equals a to y equals b. Again, similar to area, where your a value is going to be your lowest y value, in this case 0. And then 4 would be your b value. So lowest to highest, always lowest to highest, x or y. And then still we're summing up cylinders, so pi r squared. And if we want to write the function for r, this time would be in terms of y, so f of y. Sometimes you guys might see it like that. So that just means that your Your whole entire equation should be in terms of y, including this being dy. And remember, the dy is denoted as the height of each one of those cylinders, or when you draw your representative rectangle, it tells you, okay, well, each one of the widths of the heights of the cylinders is going to be dy, change in y, small change in y. And so if we picture all of those disks getting shorter and shorter, then what we have is an infinite number of disks, and that's what an integral represents, right? Summing up an infinite number of disks where the change of y is getting smaller and smaller. All right, so let's take a look at a question where you guys are given, and let me help you guys dissect what the question is saying. So it says, find the volume of the solid generated by revolving the region bounded by y equals square root of x from 0 to 1 about the x-axis. So you are responsible for sketching at least what you guys see on the left. Okay, some people like to draw like the circle itself as well. Someone had a question, so let me just make sure. Sorry, the r squared is f of y squared. So that expression would replace r squared. You wouldn't square it twice. So all of this would replace all of that. Okay, so then we're spinning it about the x-axis here. And they did give you guys a boundary of 0 to 1. And so what I would immediately do, if it wasn't already done for me, is draw a rectangle. So if it's about the x-axis, this is going to be how I'm going to visualize that rectangle being spun about the x-axis. And that immediately tells me that this is dx. So what I go on to do is write my volume with respect to x, so v of x, is equal to limits of integration for this problem would be 0 to 1. Pi inside or outside, it doesn't matter. I usually pull it outside if I just didn't have space right there, but pi, and then r squared. So we go back to the picture. When you look at your rectangle, that is your radius. That's going to represent your radius. So what you're going to do is look at the top of that function, and if everything's in terms of x, this is y equals square root of x. So my radius is going to be square root of x minus this x value. What is this x value right here? I'm going to say that I'm going to do that anyways for now, just because it's going to make the next part of the notes easier. Technically, the above formula doesn't have minus 0, but I just want you guys to think of this physically. If this represents my radius, then it's technically the length of this would be square root of x minus this x value, which is 0. All along here, it's 0. So when I write my radius squared, actually, maybe I'll just write the formula for you guys here, and then I'll make this an extra step. Okay, so r in this case is square root of x. So square root of x minus 0, or just square root of x squared dx. Now, you guys can imagine why this section is, a lot of it is in the calculator section of the AP test, because there's very few problems that when you go on and do the math of this, that you can actually find the antiderivative without the calculator. So we keep it very basic and simple with the functions, because if you complicate the functions, you won't be able to find the antiderivative without a calculator. And so I want you guys to just get comfortable with setting up the equation, understanding what's represented here before we attack some of the AP problems, which we'll do more of next week and then when you guys get back from break. So simplify always first, and you guys get x. And then can you guys finish off the problem? What is your final answer after you guys find the antiderivative of that? Plug in 0 and 1. Can you guys type in your answer? Also, as I give you guys time to finish this up, and please type it in so I can know if I should move on as well. I'm going to say again with this that your volume always needs to be positive. It's actually representative area and volume in this chapter of physical representations of things. So you want to make sure that the volume of something is never negative. If it is, go back, check your bounds, go back and check your regions and see if you guys set it up correctly. So waiting for a few more. Annie, that's fine. All right, you guys, good. So the correct answer is pi over 2. Very nice. And then if I've moved too fast, let me know as well. In most cases, you guys are not going to have a graph given to you, or sorry, you're not, you're on your homework assignment, you're going to be expected to know how to graph certain things. I would say this is not something that is unreasonable for you guys to just guess as to what the graph might look like. However, I think on the AP for response, it would take way too much time for kids to do what they consider non-AP stuff like graphing. So what happens is they'll give you guys funky equations. They'll give you the actual graph itself, and then they'll ask you guys things about area and volume. And that saves the it bypasses that problem of what if someone graphs it wrong, then the whole problem is wrong. So oftentimes the region is given to you guys, which is nice. So in this case, they want you to find the volume formed by revolving this region bounded by the graph of square root of sine of x from 0 to pi. So I'm just going to do 3 quick points and get a rough sketch of what this graph might look like. Okay, so at 0, I know that, so some key points are at 0. If I plug 0 in, I would expect that the square root of 0 is 0. I also happen to know pi over 2 gives me a nice value. What happens when you guys plug in sine of pi, or plug pi over 2 into this equation? What do you guys get for that? So if this was pi over 2, what is pi over 2, sine of pi over 2, square root of that? Okay, perfect. And we know everything before that is positive as well. So let's say this is 1. Sine of pi over 2 is 1, square root of 1 is 1. And then at pi, we once again reach 0. So roughly speaking, let's say we're above the x-axis, and this is my curve. Okay, so from there, now it says bounded by the, rotate this about the x-axis. So that's going to be your axis of revolution. So what we're going to do is draw a representative rectangle, and that's all you guys really need. And then you just go from there. Okay, so there's my rectangle. If I look at this as a really small change in x as the height of each one of those cylinders, then I know, going back to my equation, that this is going to be volume with respect to x. I'm going to go from 0 to pi, left to right, smallest to biggest, A to B. And then pi r squared is my formula. So here is where I'll point out, not for the first time, you guys, that one really common mistake between area and volume is when, after I teach volume, is when kids do area, they start to put pi's in their answer, or they think, oh, I need to put a pi in my answer. It looks wrong. Let me put a pi there. The AP readers know that, so they'll have those decoy answers with pi's in it for area. So just be careful of that trick. And then also forgetting pi when we're doing volume. Okay, so if we're doing volume by solids of revolution, if we're revolving something about something, we're going to picture circles, and every circle area or area of a circle has a pi in it. Okay, so we have pi, and then r squared in this case. R is the top of my representative rectangle minus the bottom, and the y value for that is given by the function. So square root of sine of x, and then don't forget to square that because the formula is pi r squared dx. Can you guys go ahead and complete the problem from there? And type in your answer once you do. As you guys type in your answer, there was a question in the chat. Is the radius changing because the height of the rectangle lengthens as x increases? Yes and no, but I think I get what your question is asking for. But if we think about the first cylinder is going to occur right around where x is equal to 0. And then we sum up an infinite number of cylinders that go all the way to 1. And yes, each one of the cylinders the height of the cylinder, or sorry, the radius of the cylinder is going to be dictated by whatever the y value is of this function right here, of this top function. So it does change in the sense that you guys are going from left to right. So it will increase until it gets to the max right there, and then the radius will decrease all the way to pi. But that's taken care of when you guys substitute in the function for r. Can you guys double check your answers? If you got a negative answer, always double check. It should be positive. So just check your signs. When you plug pi in, maybe that was the case. Cosine of pi is -1. So then a negative is positive. Yes, the correct answer is 2 pi. Very good. And let me know if you guys need more time. Yeah, that one's a common unit circle question that people make mistakes on. Cosine of pi is -1. Think of the x value at pi. All right, you guys, let's see what happens when we change things a little bit. Okay, so here we have find the volume of the solid formed by revolving the region bounded by the graphs of the equation about the y-axis. So this time that's going to be about the y-axis. So you guys are going to go to your y-axis, draw a little circular rotation there. And we notice that this equation is incorrect. It's supposed to say x equals cube root of y. And the function that is given to you guys is what you would see if you guys were to graph y equals x cubed, because you guys can also solve this for y equals x cubed and get that function as well. But it does say that you want the region to be bounded by the graphs of y equals 8 and x equals 0. So x equals 0 is the y-axis. That's this right here. Y equals 8 is from above. And then you have the function itself. And so the only region I'm looking at is here. So what we're doing is picturing our disk. This time you guys have your pencil being held vertically. You have a piece of rectangle taped to it, and then you're spinning that about that pencil. And the shape that emerges is over on the right. So what we're going to do here in this case is now draw our representative rectangle, go to the rectangle, and then recognize that the width of each one of these cylinders, which is marked over on the other side as well, is a small change in y. And so that's your dy. And that tells you guys that the volume is going to be with respect to y. And that changes everything to be in terms of y, including your limits of integration. So your lowest y value here happens to be at the origin, so y equals 0 to y equals, and you don't have to write y equals 0, y equals 8. Typically you don't, just because it's in the first example I am. So just keeping in mind everything has to switch over to y. So if you do have to find intersection points, make sure you guys are using the y values of those intersection points. Our formula always, we're thinking of discs. Discs are circles, so pi r squared. Okay, and then when I go to think about my radius, I can sketch a circle if that helps me to visualize things. Okay, and the radius is determined this time by right minus left. Okay, so whatever the right function is, so this function minus this function here. Okay, so if I think about this, this is x equals 0. This is x equals y cubed, or cube root of y. So in my integrand, I'm going to have the right value is always bigger than the left value. So cube root of y minus 0, or just cube root of y squared, and then dy. There was a free response question. I can't remember if it was you guys or if it was the other period, but we had to integrate something that had an exponent that you guys had to convert. There were a few mistakes on the conversion of cube root of y squared into exponent form. So just remember whatever the exponent is, in this case, the squared part, that's your numerator, that's the 2, and the denominator is your radical part. So cube root would be over 3, square root would be over 2. And then there were some mistakes also on integrating this, just exponent form. Some people did ln of y to the 2/3. Okay, so you have a power rule here. So you guys have something to a power. So the power rule, the reverse of that is you're adding 1 to that, which would get you guys y to the 5/3, and then multiplying by the reciprocal of 5/3. Yes. so 3/5. Can you guys go ahead and complete the problem from here? And remember that you guys can take the cube root of 8 before you guys take it to the 5th power. And I'm just going to say, for the purposes of your AP test, you want to make sure you guys go one step further. I had some people leave their answers after they plugged it in and then just not even simplify it, which is okay to do on a free response. Okay, so if you guys end up with a free response where you have to do arithmetic where you're just plugging in the 8, you guys can leave your answer. So for example, I see Brandon left his answer as like 32 times 3 over 5 pi, like that. That's technically correct. You do not have to write it as 96 pi over 5. However, if it is a multiple choice question, they always present it in simplified form. So you would see it as 96 pi over 5. So go ahead and take a moment and just make sure you guys don't have any questions for me. So that basically completes the disc lesson. And then I'm going to just talk briefly about washers, and we're going to practice on these eventually. So let me know if there's any questions that you guys have so far. We would have had peach rings, you guys, in class. We would have had peach rings at this point. Peach rings are, if you guys never had those candies, it is the shape of a, and those are like the kids' favorites too. It's the ones that, and I thought of them like, gosh, I was going to go out and get it and then maybe pack it in sandwich bags for you guys. But then I thought, okay, that's not sanitary either for COVID. So boo on that. But, and then, yeah, so I was still trying to think of if I can somehow do the candy lab with you guys. If I can find candy that's individually wrapped, like peach rings, I couldn't have done. Oh yeah, I guess that would have been a good idea, but nobody likes the Lifesavers as much as they do the peach rings. But that's a good idea. Okay, so and then have you guys, actually, can you type into the chat, have you guys turned in any projects or gone to the front office to turn things in during this time at all? Or pick things up from the front office? I don't know if we're allowed to have done that. Because I know I'm doing like a meme project with my geometry kids, and it's like I would love to have them turn it in, but they're saying that they haven't as well. What do you guys do for, like, is anyone taking art or ceramics? Is everything digital? Oh, the tile for the tile project, that's true. I'm just worried that they're gonna get mad at me for sending 100 kids to the front office to pick up stuff. But yeah, just wondering if I should ask and see if that's okay. Oh, okay, so you do bring in your projects for ceramics. Okay, that's good to know. Otherwise, I'm like, how would they grade it? So I tried to think of a way for them to submit it without me having to pick it up, but I still would like to see the actual project. Okay, so, send a picture. Yeah, so that's what I was going to have the kids do for their art project too, for geometry. All right, we're on our last example here, and then I'm going to have you guys work on this together. Okay, so this is basically a modified version of what you guys picture when we're doing the disc method, except for this time, when you're looking at your region, there's going to be a gap between the region. So if you look at this region here, you don't have to scroll along with me, but I just wanted to show you guys this in contrast to what we've done so far. This region, if I spin it around the x-axis, there's all this space right here. So if we can picture what happens in this diagram here, when you spin first just the line about the x-axis, you guys are going to get like a cone from it. Okay, you're going to get a cone. However, simultaneously, at the same time, you're spinning this this function around the x-axis as well. And what happens is then you get a cone, but then inside there's all that hollow space. It's kind of like I don't know, it's an odd shape, but you have that hollowed out area. And so what we do is we take the idea of what we knew about a disc, we find the area of the cone, and then we basically subtract out not area, but the volume of the cone, and then subtract out the volume of the space that occurs here. And we can achieve that through what we call a washer. Okay, so when you guys are looking at a washer, there's going to be two radius. So on this picture, if you guys can trace out the bigger radius and then just point an arrow to it. For our class, I call it big R. And then same thing for the space inside. It's going to be determined by a smaller radius. So I'm going to call that little r. And that's going to go into my formula. Also, one thing to note is that now what you guys have is your pencil. This is, so the red dot is where your pencil is. So sticking up vertically through that, you guys are going to picture your axis of revolution. Okay, so if there's any space between the axis of revolution and the region that you're spinning, it's going to be a washer instead of a disc. Now I'm going to just show you guys what we've done so far and just clarify this space idea. If you look at this region that we did for example 3, this is your axis of revolution. There is no space between that region and the axis of revolution. There's no gaps. And when there's no gaps, you get a solid disk going through. You don't have to subtract down any hollowed out area. Same is true, and that could be said about the above. If I look at this region and my axis of revolution is this, then there is no gap between the axis of revolution and the region. So when I spin it, I get a solid disk going through here. Here's a question for you guys. Type it into the chat. If I took the same region, spun it about the y-axis, would it result in disks or washers? If I took the same region, spun it about the y-axis, would it result in disks or washers? Okay, so let's think about this. If you guys spun it around, and you don't have to draw it out, but if I took that same region and I spun it about, what is going to result is, yeah, it is going to be a weird shape, and it's almost like a cylinder because of that vertical line. Well, it will be a cylinder initially. That's your big R, is from here to here. Okay, but what happens is there is a shape inside here that is going to be hollowed out. So right here is where there's going to be, sorry, I'm not a great artist here, but if you guys can imagine like a CD, do you guys even know what a CD is? A CD or a record where there's a hollowed out middle, that little space right there is going to be your little R. So this would result in a basically a cylinder with a carved out area inside. So since there is that hollowed out space, and by space, this is the space, you guys. So if you look at the picture, I'm shading it. My axis of revolution is the y-axis here. This is what I mean by there's space between the region and the axis of revolution. For those of you guys who typed in disc, do you guys see why it would be a washer? Can you guys type in yes? For those of you guys who didn't initially say washer, does it make sense that it's a washer? And that's like probably one of the biggest questions I get is it a disc or is it a washer? And the easiest way is like find the axis of revolution. And is there any space between the region and the axis of revolution? All right, so let me erase all of this. And let's go back to that example, or let's go back to the formula. Okay, so in the formula box, you guys are going to picture that you have basically two formulas like we did with the other one. And again, I keep it straightforward in the sense that we're thinking of the bigger volume minus the smaller volume. So yes, Angelina, because you spun it around the y-axis, so it's a washer. So the volume is still pi r squared, but this time we have, we're going to find the volume of the big R first, so pi. And then if it's in terms of x, everything's in terms of x, including your limits of integration. And what I do is I'm just going to write big R squared minus little r squared. And so if we think about this, this is essentially the same thing as having two different volumes. So that's the final formula I want you guys to write there. But sometimes people like to have it split apart as a to b of big R squared dx minus a to b of little r squared dx. And so I see that as well. They want to visualize it as like the bigger volume minus the little volume, or condense it all and put it together as big R squared minus little r squared. essentially because you have the pi factored out. That's part of both volumes anyway. And so this is with respect to x. So everything's in terms of x in that case. Okay, so rewrite that, except for you also have volume with respect to y, and everything's in terms of y. And again, I keep the big R, little r as that instead of f of x, f of y, just because it keeps it nice and simple. And you just understand that everything has to be in terms of x or in terms of y. Okay, take a moment and write that down. Okay, you guys, so on the example 4, you have find the volume of the solid formed by revolving the region bounded by the graphs of the equation y equals x and y equals x squared about the x-axis. So whether we spin it around the x-axis or around the y-axis or any other horizontal vertical line, we would see that there is a gap between the x-axis and that region. So when I'm asking myself disk or washer, I would think, okay, I need a washer here because of this space here. So what I'd like you guys to do, and please follow this methodology. I feel like if you follow this methodology, you won't get confused. Your first step, I'm going to say, did you guys put 2 dots on your axis of revolution? Okay, if you come to me and you make a mistake somewhere, that's usually where the mistake occurs. And it's the very first step. You're going to put 2 dots on the axis of revolution. Okay, whether you want to do it in different colors or not is up to you guys. But what you're going to do is, it's because the center of your axis of revolution is, imagine your pencil over here. You guys see my cursor here? That dot is represented by these 2 dots here. Okay, so those 2 dots are to say that the radius is going to extend from the axis of revolution to 2 functions. Okay, one of the functions is going to be your big R. Your big R is going to go to the furthest function that's away from the axis of revolution. In this case, it's the y equals x that's furthest away. It's farther away than y equals x squared. So y equals x squared is going to be from that second dot to the y equals x squared function. And so the 2 things that emerges is that your big R is going to be the blue one, and then your little r is going to be the pink one or purple one. So what I then do, or have you guys do, is come up with what big R is equal to. Okay, and what little r is equal to. Okay, so big R in this case is equal to, and I'm trying to come up with what this is. So big R is defined by x, and I'm just going to go ahead and say -0 here because you have an axis of revolution that has an x value of 0. Eventually, we might move that axis of revolution, so that might affect our answer. But right now, all you guys see is x, or we'll just add in the -0 for the x-axis. Okay, so that's big R. Below that, we'll just write big R squared is x squared. Okay, little r is going to be defined as the top of your, and it's always top minus bottom, by the way, just like area, top minus bottom. So the top of this is x squared. And then the bottom of that y value is y equals 0. So again, -0. Then we're also going to square that, kind of breaking it out into steps. So x squared squared is x to the 4th. You guys will get to a point where you're good and you don't have to do all these steps along the way. But I noticed that if you don't do these, sometimes some steps could be combined, and then there's mistakes along the way in terms of how you define what r squared and little r squared is. One of the biggest mistakes I see, by the way, is taking big R and subtracting out little r with that little, do you guys see that red line that was there from the picture that I copied? Some people interpret r to be that, and that's not true. Okay, and that's because they're confusing it with area. Okay, so always 2 dots on the axis of revolution, extend out to the furthest region, extend out to the closer region, function of the region, and then now set up your formula. So your formula is volume with respect to x, because all of these are dx, And then we have pi on the outside. Our first x value is 0. Our last x value is 1, a to b. And then the formula is big R squared minus little r squared. And the mistake that I'm referring to wouldn't occur if you guys made it a separate step to do what I did here. Just because sometimes, again, people might do x minus x squared and the whole thing squared. So separating those as different steps would prevent you guys from making that mistake. So big R squared minus little r squared. And then you just integrate and evaluate from there. So pi. And then can you guys go ahead and complete the problem the rest of the way? Volume should never be negative. Let me know what you guys get. And washers are still circles, you guys. So your answer still should have pi's in it. Good, Jake. All right, good. Those of you guys typing it in. Yes, still good. All right, you guys. Very nice. So answer is 2 pi over 15 is the correct answer.